Alright, what's up guys? In this video we're going to pick up with some partial differential equations. We're going to be talking about the wave equation. So we need to show that the given function satisfy the wave equation. We're going to be working with the one-dimensional wave equation, and we're given the function u is equal to sine of wct multiplied by sine of wx. Okay, so there isn't much to this activity or problem here. The first thing we need to do is write down the one-dimensional wave equation, and I specified that it was the one-dimensional wave equation that we're going to be trying to see if this function satisfies, and that's important because the one-dimensional wave equation is different than the two and three-dimensional wave equation. In this case we're working with the one-dimensional one, and recall that that's just d squared u all over dt squared is equal to c squared multiplied by d squared u over dx squared. That's going to be the one-dimensional wave equation. Alright, so much like we've done in other videos that I've posted where we try to show that a function satisfies the heat equation and even Laplace's equation, pretty much the same thing here. All you really need to do is make sure that you know how to take partial derivatives, more specifically higher order partial derivatives, and if you can do that, then this shouldn't be anything that's too difficult to do. And then you just got to take the information, plug it into the formula, and see if it satisfies the equation. So we'll get the partial derivatives and we'll see what happens. So let's just start by, of course, getting the partial of u with respect to t. Now for most of these, obviously it can be different, but for most of these, you're going to be using a combination of the chain rule and the product rule. So what you want to be doing is making sure you're good with the chain rule, especially the chain rule, because that's really what we're going to be using a lot for this one, is the chain rule to show that it satisfies. And you're taking partial derivatives, so you also have to make sure that you know that you're treating the other variables as constant. So in a case of, if we're taking the partial respect to u, or the partial of u respect to t, when we're treating everything else as a constant, right? So let's go ahead and get that. Alright, so when we take the partial with respect to u, what do we get? Well, we'll just get wc, those come out front, remember? We'll take the derivative using the chain rule with cosine of wct, because again, we're taking the partial with respect to t. The w and the c, they come out front. When we take the partial with respect to t, we just get 1. The chain rule says that we leave that stuff in there, and then we multiply by sine of wx, which is considered constant as well, since we're partial differentiating with respect to t. So that would be the partial of u with respect to t. D squared u over dt squared is even easier, because essentially we're going to have our w out here as well, but this time it's going to be negative and it's going to be squared. We're going to multiply it by c squared, because again, those were pulled out when we took the first partial derivative. And remember, it was cosine at first, because when we partially differentiated with respect to t, we had sine here. Now that we got cosine here, well, we know that if we partially differentiate, we'll get sine. So I just bring the negative to the front. The w and the c obviously remain out there, but since we're taking the second order partial derivative, they become squared now. And then this is just sine of wct. That's the chain rule says, you just put that back in there. And again, we're treating x as a constant in this case anyway. All right, so that's going to be your first order partial derivative with respect to t, and then the second order. So pretty straightforward process here. Okay. Alright, so next thing we need is we need the partial of u with respect to x. So let's go ahead and get that. So for the partial of u with respect to x, well, the w can come out front, and we'll have sine of wct, because we're treating that as a constant, remember. because we're partial differentiating respect to x. And then this just becomes cosine of wx. So that's the partial of u with respect to x. Getting a second order partial derivative here is even easier, very similar to what we did for the variable t. Okay. So in this case, it'll be negative w squared, because again, this is cosine. We're treating this as a constant. The w, we know that's going to come out, but since we're taking the second order partial derivative, this time this is cosine, so we're going to get negative sign when we partial differentiate respect to x. So you can bring the negative to the front. This will obviously be w squared. Again, we're treating t as a constant, so the sign of wct, we don't touch that. And then this just becomes, or we multiply that by sine of wx. And all we really did here was use the chain rule. So those are going to be the first and second order partial derivatives with respect to each of the variables. Now, much like we've done for the other variables, you just kind of plug it into the equation and see if it satisfies it. So let me just quickly write it again, because we're going to probably have to go to another sheet. So the one-dimensional wave equation it's going to be d squared u over dt squared is equal to c squared multiplied by d squared u over dx squared. So let's plug it in. So we go back to what we had. So d squared u over dt squared, which is what we had over here. Remember, that was this. So that's going to be negative w squared c squared sine of wct multiplied by sine of wx. And that's going to be equal to, then we have this c squared here. And we'll multiply it by d squared u over dx squared, which is what we got down here. So I'm going to obviously put parentheses. So we'll have negative d squared, or excuse me, negative w squared sine of wct multiplied by sine of wx. So that's what we get when we plug it back into the partial differential equation. Okay. Now, if you go back and you look at what we have for our wave equation, we can easily see that both sides are equal. And so in this particular case, that means that the following function that we're given up here on top does in fact satisfy this wave equation. So hopefully you see that both sides are equal here. This side over here. Now again, imagine, now this may look a little different, but remember this c squared here, imagine that we would have w squared, negative w squared, c squared sine of wct, sine of wx is equal to c squared. Remember, this is just the same thing as that. This side is equal to that. That's what I'm trying to say. And so you just have to look at it. It looks a little funny when you first look at it, but you can easily see here, if you look back at the one-dimensional wave equation, that it satisfies. It's equal on both sides. And that's the way you tell whether or not it satisfies. So it clearly does here. So it can be a little bit confusing on the first try. So for your final answer for this, all you have to do is say, I'll put this over here, by the way. All you have to do is say for your final answer that the given function which in our case was U is equal to sine of WCT multiplied by sine of WX does, and you could say satisfy, the one-dimensional wave equation. So if your professor gives you a question like this, you'll probably encounter doing stuff like this in, let's say, physics majors. You'll take a class typically in your senior year, although I've heard of some physics majors taking it in their junior year. But it's more common to take it in their senior year. You'll take something called math methods for physics, which is, depending on the university, it might be a 1 semester or 2 semester course. At my university that I graduated from, when I got my physics degree, it was a 2 semester course. And basically, that class will, at least half of the class that I took when I was getting my physics degree, was basically on partial differential equations. So obviously this is just some basic stuff that you'll be doing. So you'll encounter this in that class for a very small portion of the time. Then obviously you'll get into actually solving some partial differential equations. But you won't really be solving a whole bunch, because partial differential equations are very difficult to solve, and all of them can't be solved analytically. So you're not going to be doing a whole bunch of solving partial differential equations. You obviously learn separation of variables and things like that, other techniques needed to solve them. But they're generally going to start you out with doing something like this, and then kind of progress you into other equations and start giving you the foundations, such as separation of variables and other techniques to solve other PDEs, giving you some boundary conditions and stuff like that. So this is the kind of just a little bit of practice to get your feet wet with some of this, and that's where you'll see it. And again, this is typically because most undergraduate universities do not offer an actual partial differential equations class. Most do not. Some obviously do, but most don't. It's not a common undergrad class, a partial differential equations class. It's not common at all. And so you'll probably start working with this if you're taking something like math methods. And obviously if your school has PDEs, then you're a math major, which is really the only people I can think would probably take a PDE course outside of physics majors, then you'll obviously get a little bit of work with this. Okay, so just wanted to give you a little bit of information on that. That is going to be your answer. So let me know if you got any questions, and I will see you next time.